All right. Hello, everybody. This is your first time meeting me. I'm Richard Tillett, and I work at UNR at the Nevada Inbred Bioinformatics Core. And I'm going to be giving a workshop with both a bit of theory instruction and a lot of hands-on experiential activity on do-it-yourself bioinformatics with BLAST and friends. Today's goal is to answer one question that's both simple and hard. And that's, what am I going to do with this? With a pile of A's, T's, G's, and C's that might as well be binary code in terms of how difficult they are to recognize to the human eye. And since they look and feel like something that a computer would produce, even though that these are the sequences that may be, not in this particular case, but that may be inside of every one of our nuclei, or inside of a phage, as is this case, or in any organism, they look like something a computer made, so let's use computers to help us grapple with them. And the tool that we'll be focusing on today for grappling with sequence information is BLAST. BLAST is an acronym that stands for Basic Local Alignment Search Tool. And it's a tool or a set of tools used to identify imperfect matches between a query, such as what we saw on the question mark slide previously, and a nucleotide or protein database. And for that given query, BLAST will report the sequences, regions, and scores that are similar. To focus just a little bit on the name, it's actually somewhat instructive. The basic is actually just false modesty on the part of the algorithm designers. Local refers to the scope of the search within the sequence itself. Is it looking from end to end, or is it looking for regions and trying to expand them? Alignment, that's the more general form of the methodology. It's attempting to take regions that correspond to each other and essentially draw a map between them. Search implies the query and target interface, wherein we have a single sequence that we are asking a question against a larger database. And tool, it's a tool. So, putting that all together, it takes a query, searches against a database, and reports the aligned local regions where there's similarity. It's based off of an older algorithm, Smith-Waterman local alignment, which itself was based off of a type of math called dynamic programming, which we won't really terribly get into explicitly, but you'll see some of the concepts, and I'll try to signpost those when you see them. BLAST itself is an elaboration of that and a speed up of that. It uses a heuristic, a shortcut, that's a word-based method. That whereas Smith-Waterman would try to compute all of the possible alignments, BLAST cheats on the front end in order to arrive to the solution faster. So, on the second letter of BLAST, the local, a global alignment will attempt to shift regions between sequence 1 and sequence 2 shown here in order to find the areas where they're most, or the shift between them that is the best match. Whereas a local alignment can break up these two sequences into regions of similarity and find those regions that are similar or identical. And so if you have a lot of parts in the middle that don't correspond at all, it won't destroy the findings of these subregions here and here. That if these are sufficiently similar, it really doesn't matter what's in here or if this space exists on both sequences even. BLAST can also find multiple alignments for your given query, sequence 1, that had a good match here on those thin lines and a very similar match on a second spot on those second lines. And so local alignment allows you to have that flexibility, that you can find multiple hits for the same subregion in your query. So, BLAST needs two things, the query, a sequence that we want to know more about. Typically it will be in what's called the FASTA format text, and it needs a database to search. And so on web-based blasts like we'll be doing here today, and like biologists all over the world are constantly doing, we'll be searching from externally maintained databases, and we'll be able to select our targets from a drop-down menu generally. So that FASTA format text file, it's the standard on which BLAST expects its sequences, and it's a very basic, very 1980s, maybe even 1970s feeling sort of format. And it's just raw text with a signifying line, what we call a definition line, shown here in blue, where you write in free text whatever you want about your sequence. In this case, these are identifiers that are given by GenBank, and the text that says that this is cytochrome B, and maybe something about the species and subspecies, and that's all on one line for a given sequence. Then any number of lines following is, in this case, amino acid sequences, the 20 or so codons, and then the sequence terminates not at the end of any given line length, but when this character is detected again at the front of the next of any given line. That'll signify, oh hey, there's another sequence in this file. So it's a pretty loose specification. You can craft these by hand, and we will be doing that today. It's not currently used because it's great and excellent. It's used because it's easy. Oh, and FASTA format files, well, I've shown here proteins, the same conventions apply for nucleotide sequences. So, back to the motivating question. Why do we want to use BLAST? Why do we have this sequence file in front of us that we aren't quite sure what to do with unless we have tools to operate on it with? Another form of this question is, what is my sequence, and maybe what does it do? Maybe you obtain this DNA sequence from an experiment and you need to know more about it. Maybe you suspect that the sequence contains either the protein or a portion of it contains a protein that might be similar to a protein that is already known to science. And perhaps you might want to compare a transcript to a genome to look at the correspondence to see where on which genome from which organism, or even just the location, so you might be able to clone it, and to find homologs to interesting genes in your favorite species. Maybe the unknown sequence that you have is your favorite species, and you need to find out what is contained within it. And the process of finding those homologs begins with BLAST. There are specialized blasts, some of which we'll cover today. Blasts at NCBI for making gene-specific primers for PCRs. Blast to sequence or to screen a sequence for common vector contaminants called VecScreen, and a comparison blast that sort of turns the query database model on its head and just compares one sequence to another and gives you detailed information on that. And that's Blast to Seq at NCBI. So, there are 5 flavors of BLAST. I think I've covered them all here. BLAST in is when you have DNA that you're comparing to DNA, or nucleotide to nucleotide. BLAST P is when your query, your unknown sequence, is a protein and you want to compare it to known proteins. BLAST X is where you can bridge this gap, where you suspect that there's a protein coding sequence, or you know that there's a protein coded sequence in your query, and you want to translate that on the fly and search the same protein database that you would have in BLAST P and get those protein results. T-BLAST-N is the inversion of that, where you have a protein query and you want to search a DNA database, such as a genomic database, and find the local alignments for that protein along the genome, with the 6 possible reading frames being translated in a local fashion. Then there's T-BLAST-X, which puts all of these possible translations together, where you have nucleotide in your query sequence, nucleotide in your database, and you want to translate both of them. So that's 6 times 6, that's 36 possible comparisons to be done, and it's generally 36 times more computational oomph needed. We'll probably be avoiding doing T-BLAST-X today because we will be doing these live on the web, and it takes 36 times longer. So, database similarity searching has the general goal of submitting a sequence of interest, finding the most similar sequences from your known database, and the hope often is that the most similar sequences may have the most similar function or some strongest relationship. Are they relatives? Do they do the same job? Are they extremely similar? Are they actually identical sequences? Now, the way that the results are reported involves an e-value, and that's the way that they're ranked. And those are values that range from the almost infinitesimally small. I think at NCBI it actually goes down to 1 times 10 to the negative 179th is the smallest non-zero number that it will report. And as you increase this number up towards 1 or above 1, it's getting worse and worse results. And the e-value is meant to signify the expectation, and that's what it stands for, that for this query versus a given database, the expectation of finding this alignment that many times. So an e-value of 1 is not terribly good. It's the expectation that you would find this local overlap is 1. So that's the null hypothesis. Everything above 1, it means that you're kind of barking up the wrong tree, that no matter how long that alignment is, it's really not unusual. The closer to 0 you are, the more likely it is that your similarity is real and strong. And this is all dependent on a lot of factors, including the length of your query sequence, the composition of your query sequence, the size of your database that you're searching, and no 2 e-values from a mishmash of methods are directly equivalent, but we generally like to see really, really small e-values. Okay, so I'm going to dive just a little bit more into how BLAST works behind the scenes, and we'll go through this, and then we'll move on to the hands-on section. So, I mentioned very early in this talk that BLAST works by cheating, by finding local alignments, by first dissecting the query into a set of words. And words are multiple letters in a row, like AGG, that's a 3-letter word. It makes an index of these words and scans a database that's already computed the frequency of these words in, and looks for matches for those words. Then it sorts and stacks the database and tries to find the highest scoring words and extends those alignments in both directions. So for for an 11-letter word here, this 11-letter word acts as a seed for extending the comparison between two sequences. In this case, it's moving entirely to the right, where we're comparing the blue sequence with the red sequence. The extension will continue as far as the number of letters continue to match. And here we're going to see the bidirectional extension of this word that that Blast may have found. And for a protein match, you might find extension on 2 3-letter hits that extend together. And this actually reflects the way NCBI programs their version of Blast. That at minimum you need 2 3-letter word hits for protein comparisons in order to initiate extension. And as a result of word seeding and extension, we generate the local alignments that may have started with 11 letters, but then grew as far as they could with matches and mismatches and the inclusion of gaps, and then terminate based on thresholds. There are many parameters that can be tuned for when you do Blast, and I might just skim through these and get back to these when we start playing with this hands-on. This is a little bit to front load. But things that you can tune, I will just mention, and we'll get back to this though. You can choose to change the number of target sequences that will be shown to you so you don't get overloaded with them. You can ask it to automatically adjust parameters for short sequences. You can change your e-value threshold so that you don't see things higher than a given number. You can change the word size. You can't freeform change the word size, but you can generally choose it from a drop-down list. Larger words means that it's quicker to compute, but that you may miss local similarities for divergent sequences. The longer the word, the longer the perfect match has to exist in order to initiate extension. You can, at NCBI anyways, you can target a given region on your query sequence and say, don't overload me with matches from just this one region. Look a little more globally. You can change the weights and penalties of the match and the mismatch. You can do the same for gaps. You can filter out known low complexity sequences. You can mask manually parts of your sequence to be filtered. And on the topic of filtration, of filtering low complexity sequences, these low complexity sequences make up about 15% of all publicly available protein sequence data. And if you don't filter for them, you may get what you think are really good e-values, but these aren't really terribly complex or interesting chunks of protein, that they may just be evolutionary noise. All right, we're going to get to the test drives. If all of the tall letters in my name are difficult to tell apart from one another, it's RLTILLETT /DIY-blast. I'm sorry? Yeah. So yeah, I made a document that's going to contain a walkthrough for what we're going to be doing together, hands-on, and it's on a source hosting website called GitHub. And just in case it's still, my name is difficult to read. There we go. So when we land on my GitHub page, my kitty cat Luna greets you, and you will want to click on the sort of blob or square over on the right for the DIY blast. This takes us to the home of the project, which in this case is this workshop here today, and it contains a pile of files, and the one that is our walkthrough is DIYblast.md. And when you click on it, it will display some fairly nicely formatted text. And this will be our guide. So when we click on the links that are in here, for safety's sake, you may want to right-click on the links and open in a new tab or a new window, whichever one you're comfortable with. Especially so when we move between databases. If we're going to be doing things at PagesDB and if we're going to be doing things at NCBI, we don't want to be closing our windows because we probably want to compare them to each other. Now, I'm not certain how many of you are enrolled in Laura's Biology 299 course, or how many of you are not, are interested faculty or otherwise students. And I don't see any laptops, except for Julie's. But I've included some prerequisite tools that we're going to download and quote-unquote install. But since you may not have installation privileges on these machines, these should be pretty light installs, and if we can download and get them to run, they will run. And these are some pretty basic tools, just a text editor and a slightly fancy text editor used for molecular biology purposes called APE. And let's see if we can get these downloaded and at least kicking and running. The idea here is that if you were enrolled in Laura's Special Topics course, you may have encountered sequence information in a context of a kind of more all-in-one package as part of the CPhages course. You may have encountered sequence information with tools that seem very specific to CPhages that have documentation like this. Related to that project, whereas with these tools we don't have to be anchored to any of that sort of stuff.
Yeah, it's working. I was able to.
I have to install it as well. So first I'll begin downloading the text editor Atom. And that's a large text editor. So download the Atom stuff. Right click, extract all into wherever you downloaded it. It probably won't stick around. And so neither of these are particularly required for doing a bioinformatic task. You could probably get away with using Notepad, but you run into issues career-wise if you rely on Notepad or Word documents for handling your sequences. You want a text editor that sort of does what it says and says what it'll do. And if you're doing cloning things where you might be using restriction enzymes, you're going to want something that allows you to map it out ahead of time, and that's what APE is primarily designed to do. But we're just going to be using it for its ability to work with coordinates in a sane fashion. Okay, so I extracted Atom, and the Atom executable should just be able to be double-clicked and run. Cool. If you land at the Atom splash page here, don't worry about much about it. We're just going to be opening text files with it or creating new ones. So you can click on the tabs in this text editor to sort of close out these welcoming things. Oh, and it starts with an untitled blank text file for us, and that's great. That's where we're going to want to be. And if you closed too many windows, just hit Control-N to pop up a new empty text file. Back to our, oh, that's cool. Back to our instructions, our guide. We're going to do an install for APE, and that download link is biologylabs.utah.edu. It's a much faster download. Right-click APE, extract all. And click OK. And we'll also get a sort of a blank document here. The interface is a bit primitive in 90s for APE, but it gets the job done. Let me know when everyone is, or if everyone is able to get that stuff to work, and I can pause here for a moment. Something went wrong with the Atom?
I thought I just must have opened the other and the same, even though I right-clicked and said start in a new tab.
Mm-hmm.
I'm no longer moving.
Oh, I'm sorry. For the download links, you can probably just click them.
Oh, okay. Download.
And so, like I said, all we're going to be using these software for is to have a clean and efficient way to copy and paste sequence text and edit them lightly in order to feed them to the various databases for blasting. It'll allow us to give unique names to unknown sequences and things like that that are just good general practices.
GitHub later?
Yeah, it won't be going down, and you can actually even contribute to it. GitHub is a code collaboration site, and this is a public repository. That's what the landing page that had a bag of files is called. It's a repository, and anyone can suggest changes to be made, and it's called pushing a commit or a pull request. If you spotted a typo and you really want to fix my page, you don't have to. Users can ask questions, things can be changed. You can always go back to the exact version that you saw here today by just looking at your notes and remembering what day it was, because that's the version that you're seeing here that's live. So if it gets elaborated over time, you can also fork everything from this and create your own and work with it from there, from any point in time. It's a really sort of powerful collaborative tool. And it makes it easy for you to just grab my stuff and keep it forever. Or grab my stuff, lose it, grab it again. So Laura, does that indicate that your Atom download went okay?
I got it, yep.
Cool. All right, so just to recap back to the very beginning, what we're here to do today is to do some blasts, and we're gonna try to find perfect and imperfect matches, similarity between a bunch of different queries and a bunch of different databases to try to figure out more about our query sequences, about the things that we're questioning. And our first example is going to be with a novel phage sequence that actually comes from the 299 Special Topics Lab, Apple Tree 2 from Phages DB. This was sequenced, Tina, you got this in 2014?
Sounds about right.
Yeah. And so this is where the right-click, open link in new tab is probably smart if it doesn't do that by default. So we're just going to kind of follow these instructions. So we're going to want to grab the Apple Tree 2 sequence from Phages DB. So we open up phagesdb.org. And we're going to search in the search box over on the top left, right by the green button. We're going to just search for it by name. Apple Tree 2. And hit enter, and then we get to the Apple Tree 2 page. We click on that hit, and we can see some information that of what is known about Apple Tree 2. You can see that Tina found it in 2014 in soil underneath an apple tree. It's a Mycobacterium smegmatis.
Virus. The host was Mycobacterium smegmatis.
Yeah. And you can see information about when it was sequenced.
You can even see an EM picture of it. If you
Ooh,
click
yeah, let's
at the
do that.
bottom. There it is.
And so in this EM, I guess we can see the capsid of the
Yep.
of the virus, and it's very long tail.
Yeah.
Is this in cell lysate or?
It's a viral lysate, so yeah, it is a cell lysate. So it's been filtered, but things like ribosomes and stuff are still there from the bacteria.
Cool. And I didn't follow my own advice. I didn't right click, so I'm gonna have to go back. All right, so from this table of PhagesDB, we can see that, that this is in the process of being annotated. Perhaps you may be working with this this year, or other sequences. I'm not certain as to.
We're doing Nicole Terra this year.
Okay. We probably could have worked with that as well, but I didn't know who its relatives were. So.
Yeah, this is good.
And so the interesting thing about this apple tree too, for the purposes of today, is one, it might be germane to what students are already learning, and also that it doesn't exist really outside of TMCC and outside of PhagesDB and the CPhages project, which means NCBI does not yet have records based on apple tree 2. So we will get some highly predictable results from some of our searches at PhagesDB, and we will get results that are of only relatives when we go search it in CBI. And so it'll sort of help us actually feel like we're doing this live, that we have a sequence that is novel, that we created or that we found, or that we simply have, that we need to ask the world about. Like, what in the world is similar to what I have? And we're just going to start with the complete 73.8 KB genome, and we will right-click Save Link As on the FASTA file. Save it wherever you like, because we're going to be opening it a few times. I guess Documents is fine for me. I also threw it up in the GitHub repository. You could download it that way if you still had the that main page open. All right, so we've downloaded the file, and now we're going to open it up in each of our text editors. Let's start by opening it up in Atom. File, open file. Remember where you downloaded it to. In my case, I downloaded it to Documents, and there's appletree2.fasta. I open it up. It has this little project bar that we can just sort of shrink or get rid of. I think get rid of. Yeah. I'll shrink it. And so what Atom is doing for us is just showing us what was in that FASTA file. You've got that definition line, mycobacterium phage, apple tree 2, complete sequence, and then many, many lines of 60 characters of nucleotide for like 12,000 lines of this stuff. So it's a big pile of sequence. Let's open it in APE. File, open. Documents, apple tree 2. Open. And so it's processing the same exact input, but just giving us a different view based off the different sort of purposes of the software here. APE has parsed the definition line and is showing it to us down at the very bottom. And so in its main window, it's just showing us the just the sequence, and it has the coordinates of the sequence starting with 1 for the first letter. If we scroll all the way down, I suggest using the scroll bar on the right, down to 73,808 at the end. So we have the full sequence loaded up in both. And we'll be able to proceed. Okay, so back at PhagesDB, we're going to use their in-house blast to sort of take a look at what's related to this genome. They have a big button. So at PhagesDB, we click the big green locally blast this genome. And it gets us to the sort of pre-flight page for the blast, where we can select options. Because it's a nucleotide query, we have 3 choices, either blast in, T-blast in, or T-blast X, versus the default database is their actinobacteriophages database as of today. and it already has our query loaded in. And we can just run it as a vanilla blast right here and see what we get. Alright, so this blast runs fairly quickly, and it might have already been pre-computed. Maybe not though. And so the blast results gives us the result of the algorithm in a couple of different views, all on the same page, depending on how fine-grained we want to get. The first thing that it shows to us is a graphical map of hits from the result of the blast, and the portions, the lines that are colored in red, are of the highest bit scores. There are also, I can see pink further down on the table, which is the second highest sort of visual category, and the yellow regions are gaps. And each line and chunk represents a given alignment on the hit table down below. So the sequence that it's most similar to is on the very top line, and when we hover over it, we can see that it's in fact itself. That is the alignment between apple tree 2, our query, and the entry for apple tree 2 at PhagesDB. While it's our best hit, it's not actually interesting in terms of a biological motivation. On the second line, we have these regions that are aligned between. We start from the left. It's a Mycobacterium phage LeBron that covers the first 40,000 bases or so, and then a gap, and then LeBron again, and looks like LeBron again. So the second line is all LeBron with the gaps in between. So the second thing that we see, if we scroll down past the graphical, is a table of the target sequences producing significant alignments, and it gives us their names and two numbers: a score in bits, which is the sort of the raw point total made during the process of alignment, where matches get positive points and mismatches get negative points, and everything's sort of in competition for the number of points that they get in order to where they rank on this list. And a lot of these, this first page of hits are all expectation value of 0.0, which means that it was, the way that the e-value is computed was below 1 times 10 to the negative 179. And so those are extremely similar hits. And if you had 40,000 bases matching or nearly perfectly matching, yeah, that's extremely similar, as is the case in LeBron.
So that's why it's saying zeros?
Zero,
that
zero.
would be perfect, or theoretically.
It's not necessarily theoretically perfect, and we'll be able to see that when we go look at LeBron.
Yeah, we know that there's differences, but
Exactly.
according to the statistical analysis, it's giving us a 0, which you said would be highly confident, or that's like the...
It's super good.
Super good.
Like it's very, very similar.
Super duper instead of it's highly confident, okay.
Yeah. I mean, it's you can basically guarantee it's with certainty that there is an evolutionary relationship or a or some kind of relationship between the two sequences, and it's the only reason that the number stops scaling at 10 to the negative 179, I think has something to do with the way that the number of bits that are stored in an operation, it just runs out of floating point bits.
So if we scroll down, there's like an E of minus 157, so that's good. But then what is like 4E or 7E
Right.
to the minus 28?
So
What's
this
that?
is a bit of shorthand that you may be seeing when you're doing BLAST only for the first time. And so if we go to, say, 4e negative 20, 4e negative 20 means this. It's 4 times 10 to the negative 20, and it's just a more compact way of writing that.
Okay.
So that would be 0 point, a lot of zeros.
4.
But not 0.
But not 0.
So 20 zeros after the dot, and then, oh,
But we want it better than negative 50, right? So this wouldn't be,
it really depends on the kinds of questions that you're asking. If you're looking to find all of something's relatives, this may still be something that you would want to include. BLAST doesn't presume to know exactly what you're searching for. If you're trying to find the closest relative or all of the relatives, or maybe this relative, whichever one of the 5 that are 4 times 10 to the negative 20th is maybe the one that is most well known. Maybe it's been studied since the 80s, and you'll take those hits because this one has the most densest information that you can sort of lift from. And so it's a very long hit table. We could shrink that if we had told it to limit the number of sequences to display from us, but it's showing us the top 100. And I wouldn't suggest scrolling down terribly far in this interface because the third way that it displays information is with the pairwise comparisons. And you'll see that the first pairwise comparison is apple tree 2 versus apple tree 2. And the number of identities is 73,808 out of 73,808, 100% identity in the same alignment, plus strand to plus strand. So what plus is the sequence as we fed it to it, as in AGC. Minus would be the reverse complement of that, the opposite strand. We don't want to be scrolling forever because this will show us all 73,000 5 lines at a time. So to actually get at LeBron, which has a very good score as well, it's our second best hit, but should have some differences, we can go to it on the on that hit table and click that little hyperlink, and it'll move us to where that is on the page. And so we click on that link, that blue link for LeBron on its bit score, and we get moved to there in the page. If you scroll up slightly, you can see some of the secondary alignments between Apple Tree 2 and itself, from regions of ancient duplication or whatever that are not perfectly conserved, but they're sort of chatter that's left over. And if you remember from some of the very earliest slides about local alignment, just because we got hits for the complete sequence doesn't preclude us from getting local alignments of subregions in the reverse orientation. And so, to focus on LeBron, we look here at the description of what LeBron is. LeBron is a very similar length, 73,453. It's either 400 more or 400 less than our Apple Tree 2. 99% identity, all but 200 sequences, 18 gaps, and we can see that the largest local alignment between the two starts at 15,000 and I think goes to 40,000, so we could be scrolling for a while. But if you take a look at the display here, on each line you have the query and the coordinates, the subject and the coordinates, and anywhere where there's a line drawn between them is where an identity is, where the sequences are identical. Where you have a lack of a line between them, that's a mismatch. And where you have strings of dashes, that's a gap in the way that BLAST computes and renders the results.
Yeah, it might be like LeBron has an insert there at.
Exactly,
Which Apple Tree 2 does not.
LeBron has 9 letters starting at 18,400 and something that Apple Tree 2 does not have, and then the matches pick back up again after those 9 letters. If a gap gets sufficiently long, depending on the way that you've tuned the BLAST algorithm, it'll actually get broken into subregions of hits that it will make a new entry and say, oh, it picks back up again at 25,000. So a 10,000 letter gap will generally break it up into 2 different alignments. A short gap of 9 letters on a sequence that's this similar gets sort of padded by the way the algorithm has been instructed to inform, sort of. You can kind of control it, and also by just the weights and the penalties. So we can see that LeBron is, what we saw in the summary, it's 99% similar over the 25,000 sequences that were, or 25,000 letters that were being displayed here. Now a little find and replace trick. This is just going to be a find trick, though. We can use the find in our web browser to keep on looking for the additional secondary hits. Because if we remember from the graphical hit table, we saw that LeBron had 3 or 4 regions that were matching. And the trick should be to use the find function, which is Alt F, nope, Control F. And if we search for the word capital S score, space equals, space, we should be able to move down from the orange highlighted one here, score. The 7th one should be the next subregion of LeBron that hits. And so that's another 13,396 letters that were aligned with a single gap somewhere within them, 98% identity. And you can also note that the sequence regions are pretty similar to each other, that we're 486 on the start of this on our query, 514 on LeBron. So they're both at the beginning of their genomes, moving on to to 13,000 letters later. The ones above, the longer match, was between 15,000 and 40,000 in both cases. And that's an additional, like sort of that's an arrangement similarity, that their genomes are organized in a similar fashion. There's a third alignment that tells a similar story. They're getting less identical though in these regions. The bit scores are smaller, so it's either a shorter alignment or less perfect alignment, and in this case it's both. It's almost 13,000 letters aligned with 98% similarity. So this is a region that's diverged between the two. The 4th best is shorter but better. 6,600 aligned, 99% identity, so the similarity has picked back up again for this chunk of the genome towards the tail end of it. The next one, again, the same story, and it goes on. So we have this representation of the discrete local hits between LeBron and Apple Tree 2 displayed for us to suggest the relationship. And so it's big and cumbersome because this was 74,000 letters versus 73,000 letters, and we've got all of it displayed here on this page. We're going to do this similar operation at NCBI using the sequences that we downloaded, and we won't hopefully have to be skipping past Apple Tree 2. We'll be jumping right to the best entry as far as what NCBI knows about what's been published with them. So if you open a new tab to go to the NCBI homepage, on the right in the popular resources, there's BLAST. You can click on that. We get to the BLAST landing page that shows us a bunch of different blasts, kind of reminds you what you might want to be doing, nucleotide versus nucleotide, protein versus protein, one versus the other. We're going to be doing nucleotide versus nucleotide. And in terms of interfacing with what we get on this query creation page, we can either paste in the sequence that's in our Atom window, or we can just upload the file that contains it. And it's really up to you. What do you guys vote? Do we want to paste or do we want to upload?
Paste.
All right, let's paste. So we go into Atom, and we want to select all, which is in the edit menu, select all, or Control A if you're into keyboard shortcuts. And then we're going to want to copy it, which is edit, copy, or Control C. We go to our browser window. We can right click paste or Control V. And you can see that there's a little bit of cruft at the end of our file from what we downloaded from PhagesDB. For some reason, there's 2 blank lines. NCBI's parser is probably smart enough to deal with them and get rid of them, but they really shouldn't actually be there. If we click out of this box, once it's no longer yellow, we can see that, again, their parser is smart enough, and it titles our job with whatever was contained in our definition line. And that's actually the motivating reason for us to be using a text editor. And another example that I give, we're going to be naming our sequence ourselves, and so that'll sort of get in the job title. And if you're doing a pile of blasts in a day, in order to really figure out or zoom in on a handful of sequences, being able to go through your results and your recent results and looking at titles is a great way to be able to not lose all of your stuff if you accidentally close a results window and like get them back within 36 hours when you actually did the search. So doing the titling, doing a little bit of like unknown sequence 1, unknown sequence 2, whatever it is, like can help breadcrumb you back to where you were if you get a power outage or whatever. And we're going to just go with the defaults at NCBI. So that means that it's going to be searching against a database called NR. And NR is their sort of, NR/NT is their everything collection of sequences that have accession numbers at NCBI. It used to mean non-redundant was what NR stood for, but it's not non-redundant. It was non-redundant in the 80s. And it has 3 programs that it can choose from: Megablast, Discontiguous Megablast, or BlastN. And Megablast is like 100 times faster than the other 2, and we're doing a huge genome search. It's way more sensitive to gaps. That's why they have a discontiguous version. It's slightly less sensitive to gaps, but it's looking for extremely long sections of similarity. And so it runs faster, and that's good for us. So we'll just run Megablast. Check on your parameters. Open up that little box and just sort of skim through here and see that nothing is yellow, and you know that you're using the defaults for Megablast, that you haven't had any cookies set that changed it based off of, I mean, you don't, because these computers were just opened up, but it will highlight in yellow anything that you've changed from the defaults, except for sometimes the text boxes.
And on the filters and masking, and it's just low complexity regions, but there's a species specific repeats for, so would you use that if you knew like what you were looking for, or should you never use that? Or?
It's really specific to the task at hand. I almost never end up clicking it.
Okay.
The low complexity filtration seems to be good enough for general purpose use, but if you're really trying to avoid transposon sequences in a mammal, in any of the like 20% of the genome, that's those. Some of those aren't picked up in the low complexity region, and you want to filter against those. So those are your lines, your signs, your ancient transposon sequences that are just scattered everywhere. It also includes some of the repeats for ribosomal subsequences, I think, subcomponents, maybe, in those species-specific repeats.
Okay.
Filtering for low complexity regions is good for general purpose stuff. If you're really trying to avoid transposons and similar, or you have extreme repetition of some other type, you may wish to click that option. Generally, good advice is start with the defaults, and if you get a hit table that's full of garbage, that's when you start consulting your options. I should make a slide that says that actually. Alright, and we click blast. And while it's running, we get to this format request status that updates every few seconds or whatever. And if you can nab it before it actually completes, you can click on the recent results, and this page won't be updating every 2 seconds, linking at you. And you can manually refresh this and see this recent query. If you had a pile of recent queries, they would be stacking up here with the most recent at the top. If I refresh the page, it went from running to done. So I can click on this series of letters. Yours will be different, and you can get to the blast results. If your results if you didn't get to do that that landing page thing, this is the page that you would get redirected to anyways. And so this is pretty similar to and organized in a similar way as was at PhagesDB, where there are the 3 sections of our blast results. We get the graphical representation, we'll get a hit table, and then we'll get the pairwise sequences. If you're ever uncertain about what options you used, maybe you didn't make some specific name for your query. If you went back and were playing with options, you can always check the what was used by opening up, expanding the search summary button. It'll show you the parameters that were set, and these are the defaults for MegaBlast. This is a very large word size, 28. Won't ever show you anything with an expect value above 10 as a default. Will only show you the top 100. And in terms of those bit scores, things get 1 point for matches, -2 points for mismatches. Gaps don't cost anything. Low complexity filter, and some statistics that I'm not going to attempt to cover. So at the graphic summary, we get, we don't have on the top line an unbroken string of apple tree 2 matching apple tree 2, and that's expected because apple tree 2 was invented, well, it wasn't invented by nature, but it was found here, and it's not there at NCBI. And NCBI has a record for Joe Dirt here on the top line with a very long match at the left side of the genome, some other matches all the way through to the end with some substantial gaps at like the 65,000 mark. Note that NCBI doesn't have a record for LeBron yet, so in the process of the CPhages courses being administered around the world, sequences get added, genomes get added. So at some point LeBron will get added to NCBI and it will show up in the
It
results.
showed
The
up number
second one.
2.
Hmm?
It showed
second
up
one.
number 2.
Oh, it did?
Yeah. I was gonna ask why.
Oh, yeah,
They
so
put
there is LeBron.
Joe Dirt on top here and LeBron on top on Pages TV, or is the order that we see these relevant?
The order is generally by bit score here, where it's by e-value first, but these are off the charts on e-value.
Right,
And so then ordered by bit scores is secondary. But they're very close.
Yeah.
It's interesting, there's 4 of them that have exactly the same beginning,
Mm-hmm.
those first 4. Exactly the same.
Yeah, so, I mean, this would suggest something about the relationship between these phages and also the genomic content of that half of the genome. That there's obviously something that is non-conserved after the 42,000 mark that is different from one species to another. And that may have something to do with host specificity, or it could just be different piles of cruft in between. Generally, parasites and phages of parasites don't have cruft, though, or they don't have nearly as much cruft because they're under selection pressure to not have their genomes expand. That's a hypothesis to be tested and proven, though. There may be genes in there that are doing the work of host specificity, or it may be accidental recent pickups of genetic material from their hosts, or random mutations that have just accumulated in a region that didn't have something vital to the operation of the phage.
And these phages are found in vastly different parts of the country.
Yeah, right?
Joe Dirt's in New York, and LeBron's in Virginia, and Apple Tree Tea was in Nevada. Although I guess the apple tree could come from some other state, right? Or the dirt, or I mean, right? I mean, if they're, it's of course asexual reproduction, so you don't like think of it like we do
Mm-hmm. Yeah.
humans, but it's still interesting to think that.
I mean, this apple tree was planted on purpose at some point, right?
Yeah,
So that means that where was the dirt,
right.
right? Like, could it have come from the same dirt supplier, or from a dirt supplier that's nearby these natural reservoirs of relatives?
Mm-hmm.
You could potentially geolocate, and I saw that there were those sort of geolocation stuff, but unless you know who planted the apple tree, it's going to be hard to track
And a
down.
nursery.
Yeah?
Yeah. Tina bought my house, so before it was Tina's apple tree, it was my apple tree. And we went to a nursery and put it in the backyard.
Yeah, but I bet they don't know
No,
where
I
they
know.
got their dirt from.
Probably
So
not.
that'll be
It's
hard.
just, yeah, it's interesting, yeah.
So yeah, when we're using sort of a Swiss Army knife like BLAST, it's both the regions of similarity and dissimilarity that are potentially of interest to us when we're talking biology questions. And I suppose that's different than the inner workings of the algorithm questions, right? Like, we want to see our algorithm performing really well, like being discriminatory, but it's when we want to focus on the biological questions, sometimes it's the gaps that we're after. Sometimes it's the solid lines. We'll get to a hit table here that sort of shows the ordering of these top 4 hits: Joe Dirt, LeBron, UPIE, and Fezzik are just heads and shoulders above all of the other complete genomes as far as NCBI knows. They also have extremely good e-values, and we get our top 100 hits. You can see NCBI has a lot less diversity of microbacteriophages from the fact that our e-values start getting really poor here in the lowest parts of the 100 versus what we had at PhagesDB. Although that's not a It's not a full apples to apples comparison because we did let each one use their default algorithms, and normal blast-in was used at PhagesDB, whereas the speed optimized one was used at NCBI. But I think I'll stand by that statement that PhagesDB has more sequences that are more related than what NCBI has. In general, NCBI has just a slightly prettier, more updated version of these kinds of results. What you see at PhagesDB is actually what NCBI's results looked like back in like 2007. They're slightly prettier now, a decade later. I'm actually going to take a slight break from talking and have the coders at NCBI. I'm going to play 2 little videos, like 3 minutes each, about the eValue questions, because before we get much deeper, it's kind of important to just make sure we're solid on that, because they're the most frequently asked questions that I ever get, like either when doing seminars or just people dropping in throughout all of graduate school. It was, what does my eValue mean? Where's my eValue cutoff? And the answer is that we just try to make rules depending on the task. And that's true even for the people who make the algorithms. So we're not just being lazy and evasive. I'll click the YouTube links because I think the audio's piping, and I'll take a seat and drink my tea.
This is a simplified guide to any use of expect value as provided by BLAST, basic local alignment search. I'll start with that if the alignment is not due to chance, then it may be due to a biologically meaningful relationship between the 2 sequences. Does a low e-value like this prove that the 2 sequences are homologous? No. BLAST does not measure homology, but you might infer homology from good alignments like this. Another common question is, how low an e-value do I need to say that 2 sequences are related biologically? There is no single answer, because e-values depend on query and database lengths. At NCBI, we use a cutoff of 1 times 10 to the minus 6 for some internal processes using.
That's an extremely lenient value. That's what they're talking about as their upper limit for hypothesizing a relationship, either in function or history or evolution. The further away you can get from your limits that you choose, the more confident you are. The closer to 0 your e-values, the more confident you are.
BLAST P against the BLAST NR database, but that may be too restrictive for your purposes. So, the primary use for e-values is to help answer the question, is this alignment meaningful? Another use is to limit your BLAST output by setting an e-value threshold. If you only want to see results with e-values better than, say, 1 times 10 to the minus 6, then enter 1e minus 6 in the threshold text box. Finally, since my example is in BLAST P, I have to mention compositional adjustments. These statistical calculations are applied by default to provide more accurate e-values based on the amino acid composition of the 2 sequences being compared. Use the help icon to get further information and references. In the separate video, Expect Values Part 2, I'll answer some common questions about e-values that we get at NCBI.
We'll let this autoplay. This one's only another couple minutes.
In part 1 of the companion video, I gave a very simple explanation of expect for e-values and how they are used. Here I'll answer a few common questions about e-values that we get at NCBI. Question 1. How are scores and e-values related? In simple terms, the higher the score, the lower the e-value. This makes sense in light of the simple definition of e-value, the number of hits you expect to see by chance. It also makes sense if you think of e-values as a false positive rate. Take a look at formula number 3 in the Statistics of Sequence Similarity Scores, which has a link on the BLAST help page. In addition to defining a normalized or bit score, formula number 3 also states that e-values are proportional to the product of the query and database lengths. The current BLAST programs subsume this product in a calculation called the effective search space. The practical implication is that e-values cannot be directly compared when searching different databases. Even identical alignments from searches of different databases will receive different e-values. The bit scores, however, remain the same. Question number 2. What is the highest or poorest e-value that I should consider as significant? This is one of the most frequently asked questions about e-values and the least answerable. There is no magic cutoff. You will have to decide what is significant based upon your goals and sequences. Let's look at a couple examples that may help clarify this point. In a typical BLAST P-search with a query of 100 amino acids against a large database like RefSeq protein, the full-length, 100% identical alignments might have e-values of 2 times 10 to the minus 61 or lower. Note that in BLAST we tend to use the notation 2e minus 61. But what if you search a large database with an 8 amino acid query? The best alignment you can get is 100% identical over 8 residues, and that is likely to have an e-value around 1 or higher. If what you know or hypothesize about that motif is consistent with the biological function of the database sequence, then the alignment may indicate biological relevance, even though such relevance cannot be inferred on statistical grounds alone. I mentioned in part 1 of the companion video that at NCBI we use a cutoff of 1 times 10 to the minus 6 for some internal processes using BLAST-P against the BLAST-NR database. But that may be too restrictive for your purposes. Question 3. What is an e-value of 0.0? E-values are written as 0.0 if the calculated value is less than 1 times 10 to the minus 179. If you have other questions about BLAST, write to blast-help@ncbi.nlm.nih.gov.
I'm half deaf, so I can't necessarily know if we're out of static yet.
We're good, yeah. It seems good.
Okay. So was the nameless voice from NCBI at all helpful, or was it continuing to be evasive about what you need?
That's kind of like how statistics are, right?
Right. I mean, the statistics are just simply numbers that can organize our list in relation to the parameters that were fed to it. We change any one thing, and we change the question that we're asking. So the statistics can't provide us our hypothesis. So our hypothesis has to inform our statistics. And it feels like a bit of a cop-out when you're just trying to find your sea legs about these sorts of things. To be, well, what's my cutoff? Be extremely conservative. When in doubt, be conservative until you find a reason to reduce your stringency. As you showed, that there may be a reason when you're having an 8-letter query of apolipoprotein from human to chimp, if that's your top hit, even though that e-value was practically 1, was this is expected by random chance, the fact that you know that they're both apolipoproteins would inform that, yeah, hey, these are also already similar. So you can combine the statistical information with other sources of knowledge or inferred relationships, and you can use that to lower your thresholds depending on your task.
I had a question and then I stepped out.
Mm-hmm.
But when we were looking at the a sequence providing significant alignments
Is that
in
the
NCBI.
is that this hit table or is that
Yeah,
the graph?
that hit table.
Yeah.
And then if you scroll down a ways, you see pretty quickly that instead of phage, we end up seeing bacterium.
Right.
And so I wondered, like, I mean, if you were doing some kind of a project or something,
Mhm.
is that meaningful? I mean, the E values are, 10 to the minus 14, 10 to the minus 13, 10 to the minus 11, but it would still maybe suggest that the phage genome and bacterial genomes have similarities.
Right, right. And these similarities are imperfect and short, right? That so in addition to the E value, pick one for me. Pick one of these results and just name it.
So looks like there's a Mycobacterium avium 104.
Okay, cool. Mycobacterium avium 104 complete genome has a 3 times 10 to the negative 12th E value for this comparison between apple tree 2 and this, with a bit score of 91.6 points essentially for that alignment, and an 87% homology across that region. Because that score is so low, I know that this isn't a terribly long alignment. I'm going to click on the name of the Mycobacterium avium, and it should drop me down to where that is on the page. And yeah, it shows me what I expected, that this alignment is just 72 letters in an 83 letter region that that seem to be matching with these little point mismatches, 11 of those mismatches in a single gap.
So would you, it isn't showing like human sequence, but you've got like this bazillion genomes or bases in a human sequence. Wouldn't some by chance match
Yes.
up to these? And so.
Yes, but we only get to see the top 100 hits. So whatever regions of the human genome that may have short matches would be down much lower. And we probably wouldn't be able to get those with Megablast, because Megablast is really tuned to find things that are like 97% similar across their lengths. And if you're going much lower than that, it gets a real drop off in its performance. And that's great for your first pass. It's great for limiting the amount of junk that you want to see when all you care about is things that are extremely related, and hoping maybe to just borrow information that's of well-studied. Like if you have unknown versus well-studied and you just want the best, Megablast is going to provide you a lot of those really good alignments. So will Blast In, but you might have to actually go search for it, and Blast In will find little subregions that that Megablast might not because of its long word size. Let's test this. Let's switch our algorithm to, let's not switch our algorithm, let's keep it at Megablast, and let's do some restrictions on the query to actually only look for human genome sequences. And let's see if Megablast will find anything. The expectation is that we're going to get nothing. Drag this thing all the way up to the top, and we're going to go edit and resubmit. It takes us back to the query start page, and we're going to want to change the database away from NR to, how about human genomic plus transcript? So that'll give us the 3 billion letters of all the human chromosomes and the spliced transcribed sequences of the 30 or 50,000 genes that produce 150,000 different spliced transcripts. It's just sort of all like jammed together. So it's like 3.2 billion letters probably. And let's see if Megablast will find anything at all where we don't expect a relationship and where we're only going to be seeing things with poor e-values more than likely, and the noise of our algorithm trying very, very hard. Megablast won't find it. Megablast won't find things that we are expecting to be false positives for this comparison of apple tree 2 versus the human genome. Let's edit it one more time. Let's change our algorithm. Let's see if we use the more sensitive plain old blast in, and let's do that search. It should still be pretty fast because it's only doing the human genome as opposed to the trillion letter database that is in our. Trillion might be too small of a number. I'm not sure how many trillions it is. Blast in, find something. Because our database is the human genome plus transcript, it is showing us a elaborated version of the hit table with the transcripts on the top half and the genomic sequences on the bottom half. And so some Homo sapiens predicted receptor accessory protein 3, 2 variants of it, and an official mRNA claim to have similarities. But if you look at these hits, they're extremely short, 50 letters, right? And it's mostly a bunch of G's, right? Like G's and C's. So it's visually, it's, oh, hey, no, that's just a bunch of random chance. The e-value is 0.46, and that's when we're only searching against a much smaller database. So in this case, a low e-value is really kind of crap, right?
Yeah.
And so the reason that Megablast didn't find this is because there's no point where there's 28 letters in a row that match or very nearly match. So Megablast would never seed a table with any of these to find the overlaps, whereas Blast in, which only requires 11 letters in a row, can attempt to initiate an extension based on any 11-letter sequence that is shared. And it found basically one region in all, oh no, three regions. I would guess that chromosome 10 is the location of that REAP3 mRNA, and chromosomes 4 and 8 are pretty similar regions that are also just by random chance matching some 50 letters of our 70,000 letter query of apple tree 2. Actually, no, they're mapping to different subregions. So this is what noise looks like. This is what noisy, non-real results sort of typically look like. Short, lots of gaps. It's not always true. There's 25 letters in a row. Poor e-values. And no biological hypothesis can match this. Right? These phages don't infect mammals, so there's no real mechanism by which we can think that they would have acquired human sequence to be similar to. We can understand if a phage has similarity to a mycobacterium, it could have picked some of that stuff up at some point in one of the cell divisions or lytic,
Lytics.
yeah, where, oops, I grabbed some of your DNA and it made it into my capsid and now it's mine. And maybe it gets neofunctionalized. Maybe it gets a job. Or maybe it gets pushed back out. But the presumption is that if it harms the phage, if it inhibits any of the work of being a parasite, that phage won't reproduce and it won't go on. So only things that are neutral or minorly inhibitive get retained and get put to work. This may have jumped us a little bit out of order, but I like answering questions and felt really organic. So we may skip a section because of that, or we may just hit it again. So I know that I took a break while we were watching the video. Does anyone need to take a break? It's been about an hour and a half now. Stretch your legs, go potty, refill your teas. Cool.
I'm sure one of the buttons is pause. Maybe you just hit the red button to stop recording.
Oh, yeah. There we go.
All right. During the break, an interesting question came about, and we wanted to capture it for posterity. Laura?
So I was wondering, since in any of our 100 matches, we didn't see any from the host, Mycobacterium smegmatis.
Mm-hmm.
So could we search Mycobacterium smegmatis genome for phage similarities to our phage?
Absolutely. And we did check also over the break and saw that NCBI knows about at least one strain of Mycobacterium smegmatis, and we'll be able to restrict our search only for apple tree 2 versus that Mycobacterium. And let's see what kind of results we get. If you have any of our given result pages up, you can hit edit and resubmit, and we'll get back to that make your query or build your query page. So to blast in search, we see that it's our apple tree 2 complete sequence. Here's where we could be giving them unique names, and because it truncates them with ... dots, you know, for our later perusal, at least during the next 36 hours before they get wiped out, we could be versus smegmatis.
Oh, I see.
Right. And this doesn't affect the operation, just simply some of the text that will be included in your results. Like this will get shown in a couple of different places on the results page. It'll get shown on that temporary table of recent results. And that's why I moved it to the front, because that table gets shrunk. So whatever you choose to name it, or if you don't, it's up to you. We want to be searching in others in R, I believe. And organism is here where we will restrict our search only to Mycobacterium smegmatis. Mycobacterium. Okay. Let's scroll this page. It sort of does like an autofill on us. And you can see that there's smegmatis, the tax ID 1772, and then all of these particular.
And MC squared 155 is our host strain.
So would you like to look just at that host strain? Then
Yes.
we just click that, and it gets restricted only to sequences from that. Because we know that it has a genome record, there will be a genome record, but then there will also probably be other shorter records from sort of remnants of the building of that genome, or maybe the individual genes.
Right, okay.
And depending on where NCBI stores the Mycobacterium smegmatis genome, we could possibly restrict it on the database side as well. But I don't know if the genome is stored in R or if it's stored in RefSeq Genomic. It might not be significant enough to NCBI for them to include it in the short list of RefSeq Genomic.
Yeah, they do have a 16S ribosomal RNA sequence database, Tillett. Did you notice that? Yeah, they do. If you drop down menu on that nucleotide collection, see at the very, very bottom of it.
Oh, yeah.
So we do that too to try to identify bacteria. So we could just pop on that, and that would then limit us only to what's in there.
Yeah. Do you use specific primers for like
Yeah,
area 3 and area 4, things like that?
yeah, we use specific universal primers actually,
Mm-hmm.
so that way we hit as much, you know, because they're unknown bacteria that we're trying to identify.
Right. The V3 and the V4 stuff?
Oh, and it came back already and it said, no significant similarity found.
Which algorithm? Megablast?
Yeah, Megablast.
Then I'll take a shortcut and see what happens if we try to do it with blast in with its smaller word search sizes.
Okay.
And I'll just try to stack the deck as well and make it not mask for low complexity regions, right? Like there's not a biological reason why why the sequences that accidentally get stolen have to be complex. It could be stealing what is not terribly useful to the bacterium and repurposing it. We might get hints of that. But when you're looking at horizontal gene transfer, which I think is still technically the case, or host parasite gene transfer, you run up against the question of your detection limits more frequently. Your signal to noise sort of ratio is lower and more difficult. When you turn off the screening of those low complexity regions, it can significantly impact the algorithm performance.
Well, I'm just changing from the Mega Blast to the Blast 10. That's all I did. I didn't change parameters, but it's
Still running.
It's still running.
Yeah.
I get ANSI, so I go to the recent results table, and then that way I can hit F5 or Control R or whatever to have it prove to me that it's still running.
Mine says it's still running.
So yeah, by changing the algorithm to blast in, which is more sensitive to less high identity alignments, and then by also saying, show me the junk too, by turning off the low complexity filtering, we're changing the question that we're asking, and it'll be interesting to compare if we get results in a timely fashion between me and Tina.
Yeah.
But as you sort of loosen each parameter, you should dial down your expectations that you're going to find something that's biologically meaningful, or that is going to have an answer that you can use to generate like further hypotheses and leads.
Mine finished. Did yours finish, Tina?
Mine was finished.
Yours is finished?
No, I'm still searching.
I ran the same one as Tina, I think. Did you?
I think I did too. I just changed it
The
to.
only thing I changed was to somewhat similar to the very bottom.
The blast in.
Yeah.
Yeah, me too.
So since I
What
turned off.
about tRNAs? Do you think that they're grabbing tRNAs from the host? Because some phage have tRNAs and some don't,
Mm-hmm.
but they don't all have tRNAs, and then they have different amounts.
Yeah. And Apple Tree 2 has TRN.
Yeah, and that's mostly what's showing up,
That's what's showing up.
is mostly tRNAs.
Well, because that's what kind of the idea is that's where they're getting them from.
Yeah, and it looks,
But perhaps this is.
in a partial sequence to the ARG-S operon.
Mm-hmm.
But of course, the scores aren't very good. And coverage, yeah.
But I mean, we don't
But
expect.
tRNAs are really tiny
I wouldn't say
anyway.
you wouldn't
Yeah.
expect that much of a coverage usually.
Like we don't necessarily expect that a stolen sequence has the same job, like if it's from the ARGS operon, as it's moving into the phage.
Uh-huh.
Although it sounds like from the tRNAs, you are
They're useful.
hypothesizing that they're stealing the tRNAs and using them as tRNAs.
Yeah.
And so for that, you would have to really apply some tRNA specific kind of question asking that's a little bit outside of BLAST, but the concept is very similar. If you have what you think is a tRNA sequence, you use a two-dimensional motif folding tool, and I think your guys' package includes something like that.
Yeah.
Yeah, Aragorn.
Argo, yeah.
And you know, like this isn't my wheelhouse, but you would be looking for one, conservation of the acceptor site or whatever, the anticodon, and then other
Oh, okay.
like other known regions and maybe
Right, because some of the others wouldn't matter.
Right.
yeah.
Oh, yeah.
And so if the matches are happening in a way that makes like the clover leaf of the shape that kind of looks right.
And gives you the anticodon that would match up to like cysteine or tryptophan. It looks like there's one.
Yeah. Or possibly some of these tRNAs have been stolen to do some of the weird things that these phages do. Like I noticed, and this is going to give away part of the ghost for what I think is my coolest example, but I noticed that there's a gene that you're going to be searching for that has a non-canonical start codon. Like it's not ATG.
Right.
How's it doing that? Does the bacterium do that, or is that something that is specific to the phage?
Yeah.
Could something like that be caused by a tRNA that has become its a replacement or a drop-in for the methionine start sequence?
Oh, I see what you're saying, yeah.
I don't know. I'm not.
We should get to that. I'm gonna quit
All right.
comments on other things. I'm gonna shut up.
Okay, so I will get back to my GitHub page with our walkthrough. And so, what should we say for the camera? What we found out when we searched, we found regions of potential similarity. When we looked at genes that were encoded or listed at NCBI, we saw primarily aminoacyl tRNA thingies, one operon, and when in my unlimited results, I saw that there was some other gene, some glue to something synthase, but that it was primarily dominated by these tRNA genes.
Yes, definitely.
So it's a L-glutamine fructose 6-phosphate aminotransferase gene.
Okay.
21 letters of perfect match. It's not quite enough to do much at all, but it's a perfect match. All right, I'm gonna skip this section for modifying parameters at NCBI because we weren't really skipping it. We've actually done some of these as a result of curiosity. All right, now here's the puzzle portion. Let's grab a phage that we know less about, something called gumball from Phages DB, and same as as we grabbed Apple2, we're not following my advice. Right-click into Phages DB, search for the word gumball. You could also download it from the GitHub because I have it in there. But real life doesn't always have a GitHub. Oh, that's weird. It's serving me Google ads.
Yeah, I saw that.
Go below those Google ads and get to the Phage gumball page. And we're going to want to download the sequence. You can close the Apple Tree 2 sequence files if you want. If we need them again, we'll open them up again. So right click, save link as, gumball.fasta is fine. And then we will open it up in APE. Yeah. Open gumball.fasta, and we see APE's interface that's very sequence prominent for the 64.8 kilobases of the gumball complete genome. According to my instructions in the walkthrough, I'm going to claim to you guys that somewhere between the 16,320th letter of the genome and the 21,107th letter of that genome is some gene, and I may not have gotten the numbers right perfectly, but that there is at least some gene in there, and it's our job to find out what that gene is and how close to right my numbers were. And we're going to use BLAST to get us most of the way, but there's some interesting biology that's going to trip us up. We'll get really close though. So to do this with APE, and this is the entire reason we downloaded APE, is that we can do a select from to kind of select by going to the edit menu and select from to, or Control-Shift-A on Windows. And it pops up this little dialog, and because we aren't expected to memorize two 5-digit numbers, 16,320 into the left little thing, or not, maybe type it in, to 21,107. And we're going to click OK. And we'll see that in APE now it's highlighted just those regions, and we can sort of have, we know that we got it right. If we were to do this in Notepad or attempt to do this in even Atom, how do we know whether we're counting the returns or not, or the definition line? We can't, there's a variability there that we can get away from by using something that's focused, so sequence focused the way APE is. And so we want to copy this sequence, and we're going to paste it into Atom so we can give it a name. So we're going to go Edit, Copy, and hit for a new sequence, Control-N in Atom, or for a new file. Paste that naked sequence of 4,788 bases or so. And it's just going to fit on one line. And so we hit up to get to the front of that line after we paste it. And we're going to hit return so we get a blank line on top. And we're just going to give it a definition line. And, you know, whatever you want. Mystery, gumball, gene. And then we're going to copy this whole thing. So select everything. That's Edit, Select All, or Control-A. Edit, Copy, or Control-C. And we paste this into NCBI and see what we find. We're going to do a different kind of BLAST. Because I told you that it's a protein, but what we have is the genomic sequence, we're going to do a BLAST X. So go to the main BLAST page by clicking the word BLAST at the top of any page that sort of was BLAST related. And then we'll get to the arrow pointing right. That's BLAST X. And we will paste our sequence. You should see the name of whatever you named your sequence in Atom show up on the job title once you get out of that box. Genetic code, 11 for bacteria and archaea. Those are settings that are also used at Phages DB, and I figured they know what they're doing. The search database in R is fine. We know that, or we don't know if gumball is in NCBI yet or not, so we want to search everywhere. Algorithm parameters, if you see anything that doesn't look like it was the defaults, you can always hit the restore default search parameters button. And it'll give us up to 100 sequences. A e-value of 10 is the worst. It'll show us a word size of 6 for the proteins, which is the default, etc. Using the standard matrix. We have a long sequence, so Blossom 62 is a great substitution matrix, it's fine. And yeah, defaults are always good for a first pass.
And are we using the non-redundant protein sequence?
We are.
Okay. And is it okay if Mr. Gumball gene it shows up in my fastest sequence box, or should I delete that? When I
Oh, in
copy
the
and
at the
paste
top of it.
Uh-huh.
Yeah, it should be there.
It should be there. Okay.
Yeah. So what BlastX, I believe, does is it does all 6 translations possible for a nucleotide sequence, and chunks them and uses those to seed an equivalent to the BLAST-P, protein versus protein algorithm, and it can mix and match between things that are on the same strand. So I'm not sure where it makes the decisions, but it can be tolerant of frame shifts, where you have an insertion of a single or 2 nucleotides, and it can extend the alignment through a frame shift, but I think it seeds from the individual possible translation frames. I'm sure it's really cool math where they choose to do it where they can still be fast and still actually be frame shift tolerant. Not everyone who claims to do it actually pulls it off. Had a hardware manufacturer who made an FPGA accelerated version of BLAST that couldn't actually combine through frame shifts. They wanted you to pay extra for that. All right. If your results have finished, you may see what I'm seeing here, which is a different version of the graphic summary. This graphic summary has something extra on it because NCBI pre-processes your sequence when you're doing a BLASTX or a BLAST-P to look for common domains, or at least domains that it knows about and has names for, that are conserved widely, or at least somewhat widely. And it says, I don't know if you were looking for these or not, but hey, you have something that's in a superfamily or something here. Maybe you should look into this. This might be a conserved gene. And this we haven't seen before. This multi-domain family goes by the really informative name PRK0224, which doesn't tell us much, but if we clicked on it, maybe we would find something. And these are protein motifs. The things in blue are regions of that are potentially of function for like bending or twisting or making the shape or the active side of an enzyme. The way that a protein can fold and really exist as a three-dimensional object, down to the actual, like the larger the domain, the more likely that it's associated to the greater portion of the function. But really small motifs are mostly about shape. Is it a beta fold? Is it an alpha helix like keratin? Things like that. We won't even deal with it.
Boy, if you had time to like learn all this stuff, there are so many cool questions to ask with so much data out there
Yeah, yeah.
and so little known.
So we get to our usual blast table or graphical summary, and we can see that we have some full length or nearly full length matches, which means I wasn't too mean when I made this. It looks like that there's only a single gene in our query, and it looks like, at least to the eyeball, almost all of it is encoded in that gene. Our top hit is even, also from Gumball, so I chose something that's in NCBI. So hey, we get a little closer to our answer. And if we clicked on that top hit, the GP26 from Mycobacteriumphage Gumball, we can see an alignment that's length 1,590, and this is in amino acid sequences because this is a protein that is our hit. With out of 1,590 letters in this protein, there are 1,590 positives, and this is a term we haven't seen before. There's only one mismatch, and can you tell me where you might see that mismatch? If you're on roughly the same portion of the page that I am.
So, there's some.
It's on the first line.
On the first one, let's say there's some things that are in little letters instead of capital letters.
Those are masked. Those are low complexity regions that are masked. So with the default low complexity masking, it will not seed from those areas, but it will extend through those areas.
Oh, okay.
So none of those will actually show up in the very earliest phases of the algorithm. It doesn't want to try to build things from repetitive boringness, according to their definitions.
But the first one has a plus.
Exactly. So when we're looking, this is the one mismatch. But it's not a mismatch, it's a positive. So when we're doing protein-protein comparisons, the similarity matrix, in this case the default one, Blossom 62, uses a combination of like the codon tables of how all 64 letters can be 20 different amino acids. It can look at things that are off by like just a single letter in the wobble base. Well, I guess it's not wobble because wobble means that it stays conserved.
Yeah.
And also based off of the chemical properties or the electrochemical properties or the polarity of the two different sequences. If you have the two acidic amino acids, a glutamate and an aspartate, that are differing, they're going to get a plus because those guys, they only differ in like their electrical potential. They're both they have really similar pKa's. They're both going to either have the hydrogen or be like this naked minus charge, ready to do whatever, like to be acidic in similar ranges. One's slightly more acidic than the other, but they're probably doing the same job on an otherwise the same protein. Whereas if you have something like a tryptophan, that is the amino acid that's bent in a cyclic proline. Which one's bent in a horrible ring?
Phenylalanine?
I mean, phenylalanine is a ring, but which one has the, when we draw it, we usually draw the side chain on the top because the side chain is bent back over.
The proline?
That's proline. So proline generally doesn't have positive matches to much anything else because proline's job in a protein is generally to bend the protein, to end one motif and start another. So proline, I don't know if it has anything that's going to get scored a positive match in Blossom.
But a positive match would basically be tolerable.
Yeah, yeah. And not all pluses are the same. This is a convenience for the pairwise alignment. The Blossom table has the 20 by 20 scores. What's the diagonal of that? So it's half of that. That say, if this, then that, subtract this number of points, add this number of points. So you still gain points for an aspartate to glutamate mismatch. Like that's still positive. It's like these guys are so similar. Like this doesn't even count as a negative. This is still something that I'm going to award points when I'm aligning or extending. And so because of this, we have instead of like lines in between our query and our subject, we either have that plus or a blank or the actual letter, because we're using Blossom. So we just have one mismatch, and that's at the very beginning, and the other bunch of them, the other 1,589, are perfectly matched. So this is probably, this GP26, whatever it is probably the protein that I told you was in your sequence. But GP26 doesn't tell us very much, does it? If we go up to the hit table, back up to the hit table, or look at the hit table for the first time, we can unfocus our eyes a little bit and see if there's anything that jumps out at us, anything that has a name that actually looks like a word, as opposed to a series of numbers and letters. And seventh or eighth one pops out at us as a tape measure from a phage called Hawkeye. Then we get a bunch of hypothetical proteins. Those are not terribly interesting names. Tape measure, tail assembly chaperone. Like this, maybe we keep on seeing something about tape measuring and tails. I would hypothesize from this, what? Just by glancing at this, what would be my unfounded assumption? There's a tape measure. Let's click on that gumball link, and let's actually click once further into looking at what our hit is. So we're at the pairwise comparison here, and we see the sequence identity of YP underscore some stuff. We click on that, we get to that entry in GenBank, or GenBank's protein database. So this is the semi-permanent record of GP26 mycobacterium phage gumball in GenBank. It gives you all the information about like how it was sort of made and deposited, when, by whom, if it was in a paper or not, and a lot of stuff that is, wow, this is a lot of information for me to see. The source, the protein, regions that could belong to families. Those might relate to those little blue sequences that we saw up at the very top of our results for the first time. But scroll all the way down to the last feature before we start seeing the sequence, and it says CDS. So that's the, CDS is the coding sequence. So all of the letters are the coding sequence. We see 26, and we see gumball 26, but then we see in the note, someone wrote tape measure protein. So even our poorly named top hit, which is almost certainly the protein that that we queried, is a tape measure protein. So even though the name wasn't great, someone already recorded that. So sometimes you have to dive this far deep to find that information, and sometimes it's buried there, sometimes it's not. If you guys haven't covered or focused on tape measure, I think I included a link in my instructions as to what it does.
Yeah, we haven't talked about tape measure.
So tape measure has a kind of a cool job. Maybe you guys will go over this if your inquiries take you there, but it's how the tails of lambda-like viruses assemble. It's part of it. So you have this really long tape measure protein that chaperones come along and start like globbing themselves onto, and the other proteins that make that tail that we saw in the EM picture assemble into that tail. And the length of that tail is I think determined to a large degree by the length of the tape measure. A shorter tape measure can only assemble so many units of chaperone and so many units of base plate. And so our 1,590 letter tape measure tail should have a fairly strong relationship with the visible length under EM of gumball's tail. Shorter one should have a shorter tail. And if we have any discrepancy in that, that's a question we have to reconcile, right? Because we would have two conflicting pieces of information. We have what we can see on the slide, what we can see on the plate, versus what we think we know from the sequence. And they can't both be right. if they differ. So this gene that I'm giving you the example of is the cause of how tails get formed. But there's still a missing piece of the puzzle, because the sequence that I gave you should match 1590 out of 1590, not 1589 out of 1590. And BLAST doesn't give us an answer for this, but this relates back to the immunoacyl tRNA hypothesis, and that is, if we go to the gumball page at PhagesDB, and we scroll down to characterization, part of the table, and then gene list. Well, now we know that there's a gumball 26. And there's a little bit of interesting information that I glanced at when I was preparing all of this, that this gumball 26 gene is recorded to have as a stop codon, as a start codon, GTG, as opposed to the normal or the expected ATG, which encodes a methionine in most cases, and is the usual start site. So here we have, it's been recorded that a GTG is the start site. Someone, when they were creating the GenBank entries, said in this case, for this protein, for this gumball, GTG makes a methionine, as opposed to the valine that it usually makes when it's the first amino acid of the protein. So it has an alternate start site. So in fact, our BLASTX results shouldn't have a plus there. It's simply that our Blossom 62 table couldn't account for something that is biologically known, that GTG is methionine in this case. How is this occurring? Could it be any of those aminoacyl tRNA synthetases? Could it be a newly acquired alternate start codon? Could it be part of the of ribosomal function? This is interesting biology, right? Because we have the stated claim that in this case GTG is making not valine but methionine, and if someone doesn't know how or can't claim how, that's new biology for us to discover. So we solved the puzzle. It had an extra clue that maybe hints at future experiments or to learn some biology. Maybe it's just doing your background research. Maybe the mechanism is known. It's not known. Could the mechanism be from a stolen gene from the host? Could it be from something that in gumball is a newly acquired gene or mutated gene that wouldn't be found in host stolen sequences, but is hidden somewhere in its 68,000 letters, is the ability to start proteins with an unusual codon? Or is this part of the mycobacterium's biology? If you guys find out, let me know. Or if there's something similar in an apple tree, let me know.
So we do know, I don't know, how, why, whatever. We do know that GTG is a start site for mycobacteriophages, and ATG is, and there's another one. I don't remember which one it is. There's actually 3 start codons
Okay.
that they can use, but they're very rare.
Right.
Like, I think GTG is the rarest start codon.
Mhm.
They use like 1% of the time.
So that's like once per genome?
Not even sometimes.
Yeah. Yeah. Because there's like, what, 100, 200 genes per phage?
Somewhere between 100 and 300.
Okay. So yeah, from 0 to 3 times you could see that.
Yeah.
Yeah, I mean, it'd be interesting if this is something that is phage specific or if it's host related.
Right. TTG is the other start site for those sometimes.
I mean, we see some of this in some of the more well-studied alternate codons, like some lineages, their mitochondria, like of eukaryotes, their mitochondria have rare but consistently non-ATG start sites, alternate stops, recodings of tRNA synthetases to be instead of phenylalanine, it's isoleucine. There are at least like 17 codon tables in the that are important enough to be listed in NCBI, and one could construct one's own, although you're not going to be using web tools to be able to do blast keys against that. You'd have to move to the command line and provide your own translation table. I think that's where I'll end things on in terms of the combination of prepared and what you guys came up with types of blast searches. We have a few more minutes if you want to fire off some more things at me. Or we can call it a wrap. Yeah, the GitHub, I will not be taking it down. I may replicate it under my organization's name, UNR-CFB, so I may clone it and then add a link to the README file saying this one it won't be maintained anymore. Updates will go into that one, but you can keep these forever. You can steal it as much as you want. It's not even stealing.
I think the tape measure stuff is interesting. When I was at the conference, the last conference that they had, somebody had actually compiled data on the gene length of the tape measure protein versus the size in nanometers of the tail.
How did the correlation look?
Oh, it was completely correlated.
Yeah, perfectly
Yeah, and I
linear
don't
as well.
remember how many different ones they did, but they had like a graphical representation. It was really cool.
Yeah, that is really cool.
But it also, like you were saying, if you have any that you ever find that maybe don't correlate.
It would if you have that graph of where this is what people see, this is consistent, and you have the understanding that this is sort of like laying out a piece of rope, and
Right.
you can't magically grow more rope than what you laid out,
Right.
that everything's going to assemble upon. You are sort of forced to answer that question: which one of my two pieces of data can be true? Is my EM wrong, or is my sequence wrong?
Right.
So in APE, there is, under the tools,
Mm-hmm.
there's actually something that says blast sequence at NCBI. Is there any reason not to use that?
It might be broken.
Okay.
If you scroll to the top of my notes, there's I didn't actually check it because I don't know from where in the development it was, but there was a note that the blast might be broken.
Okay.
That it's one guy in Utah who makes this.
Okay.
So his notes, that warning might not be true anymore. But NCBI did just do like a huge change in their back end of how blasts happen when a computer asks another computer to do blasts, and they probably destroyed everything that he wrote because they never changed that back end before. So maybe a year before that starts getting working again.
Okay. Well, it actually.
It ran?
It did run, but the results were actually different. So
Yeah.
somehow I think the code might have gotten screwed up for this concern.
Certainly. Yeah, I mean, it could just have like, that's even worse than something failing, right? Like something failing in a way that is.
That you think has worked.
Yeah,
Well,
yeah.
you get results, you think,
Right.
oh, here's my results. Yes.
So yeah,
Not.
like the big thing that we were using APE for was to have the ability to control what we selected from a larger sequence. There's a way to do it without any tools installed. If you had that whole gumball sequence, you could have just entered those two coordinates into the search here up at the top of the query page.
In blast? Or-
In BLAST, yeah. So if we go to our results for the mystery sequence versus NR, You go to edit and resubmit, get back to the way we did it. Right up here, right up at the top, right next to where we pasted in our sequence, query subrange. So we could have done the whole
The
genome
whole genome.
and then done those numbers, and it would have only done searches through there as if the other parts didn't exist.
Okay.
Um,
So this is a way when we're annotating and trying to identify proteins, if you identify a gene in your particular sequence, you could put those numbers in and look to see if anyone else has called it a protein, right?
Or like if we're looking at, if we have gaps that we have to go in and manually search, we can do that
Yeah.
too.
Yeah, right.
Yeah, I know that a lot of your integrated solutions, or at least the ones that you were using 2 years ago, covered a lot of this sort of coordinate handling internally, so that you didn't have an opportunity to have it slip or whatever. But it's nice to have, but you don't always have that luxury. Right, like-
And maybe this would be faster than,
Maybe, yeah. I mean, this is what I did in the real world. I mean, it's not terribly sophisticated. You punch in the stuff and you don't screw up when you copy and paste. Try to be as good as a computer. And it's don't kick yourself if you screw things up. Just try to catch your mistakes early. Cool. Well, thank you guys. It's 2.5, 3 hours of stuff, and you guys stuck through it. I hope it was informative, on blast, not just for your current projects, but this is the way it happens in biology, in small labs, large labs. We use it, and it's the most highly cited paper, I believe, like currently in all of biology. It was published in 1990 or 1997, still #1, more cited than the Watson and Crick.
really?
Yeah, it surpassed it sometime in the 2000s.
Wow. Thank you.
Thank you.
Thank you.
Thank you.